In this video and the next 4 videos, we'll have a look at thermochemistry. Thermochemistry is all about heat in chemical reactions, and by the end of this video, you will have learned about the concepts endothermic and exothermic reactions, enthalpy, and how they relate to thermochemistry. And to start with, I think an exothermic reaction would be appropriate. An exothermic reaction is a reaction where heat is released, and in this old photo you can see a highly exothermic reaction taking place. Perhaps you have seen this photo before? If you squint your eyes and watch carefully, you can see that it reads Hindenburg right here. This was in 1937 when the airship Hindenburg was about to land in New Jersey, USA. The airship was filled with hydrogen gas, and for some as yet unknown reason, it caught fire. Perhaps it was a spark from this nearby tower or an engine failure. At any rate, the airship burst into flames, killing 35 of the 97 people on board and 1 additional person on the ground. Although this was a horrible accident, right now we're only interested in the chemical reaction taking place. Hydrogen gas reacted with oxygen in the air, and the reaction is highly exothermic. A lot of heat is released. Let's write that down too. In exothermic reactions, heat is released. And because I also like languages and words, let's have a look at the parts of this word, exothermic. Exo here comes from Greek, meaning outside or out from. Thermic is derived from Greek thermos, meaning hot or warm. An exothermic reaction is thus a reaction in which heat, or rather energy, is given off to the surroundings. And as an example, we take the reaction in which hydrogen is combusted in oxygen with a chemical formula I'm sure you've seen quite a few times by now. 2 hydrogen gas molecules react with 1 oxygen gas molecule to form 2 water molecules. But in this case, we also add energy here to show that heat is given off in the reaction. Now, it's important to understand that the energy isn't created. Energy can neither be created nor destroyed. It can only be transformed from one form to another. In this reaction, the energy stored in covalent bonds in the hydrogen and oxygen molecules is transformed into heat, or thermal energy, and light, which is also a kind of energy. Let's draw an energy graph here to explain what happens in the reaction in the terms of energy. On the y-axis we put energy, and on the x-axis we put reaction. And somewhere up here we indicate that we have the hydrogen and oxygen molecules before any reaction has taken place. And just to make it really clear, let's also draw 2 hydrogen molecules like this and an oxygen molecule too. Now, if we want these molecules to react with one another, we must first break the covalent bonds between the atoms in them. And in order to break a bond, we must always add energy. There is no exception to that rule. So, by adding a small amount of energy like this, we break the bonds between the hydrogen atoms and oxygen atoms. We draw it like this, and we also write that we now have 4 hydrogen atoms and 2 oxygen atoms. The amount of energy required to start a reaction is called the activation energy. We extend this line here to the left, and we also write activation energy here. As you can see, in this reaction, the activation energy is quite small. Perhaps it was only a tiny spark that ignited the entire Hindenburg airship. When new bonds form between the hydrogen and oxygen atoms, energy is released. Like before, there is no exception to this rule. When bonds form, energy is always released. In this case, 2 water molecules form. As you can see, quite a lot more energy is released than was initially absorbed. This is why this reaction is highly exothermic. In endothermic reactions, heat, or rather energy, is absorbed. You can tell this from the endo here, also from Greek endon, which means in. In endothermic reactions, heat goes into the reactants and is therefore absorbed. My favorite endothermic reaction is the photosynthesis. In this reaction, 6 carbon dioxide molecules react with 6 water molecules, and with the help from the energy in the sunlight, glucose C6H12O6 is formed. And well, yeah, 6 oxygen molecules are also released as some kind of byproduct. Let's draw an energy graph for the photosynthesis reaction too, with energy on the y-axis and reaction on the x-axis. Down here somewhere, we start with the 6 carbon dioxide molecules and the 6 water molecules. This time I won't draw them, I hope you'll understand anyway. Now, just as before, for the reaction to take place, some energy must be added. In this case, the activation energy is quite high. Energy in the form of light is added so that the bonds between the atoms in the carbon dioxide and water molecules break. I also want you to note though that the reaction is much more complex than what I show here. In reality, no free carbon, oxygen and hydrogen atoms are formed. This is just a model to show you what happens in terms of energy in the reaction. Anyway, when the glucose and oxygen molecules form, new bonds are formed and some energy is released. In this case though, much less energy is released than was initially absorbed. In total, quite a fair amount of the energy in the sunlight is absorbed and stored chemically in the glucose and the oxygen molecules. Now, I'll show you 2 fun reactions that are quite easy to demonstrate in the classroom. In the first one, I have a beaker with water and you draw this too. To this water, we add some solid sodium hydroxide, which looks somewhat like this. When the sodium hydroxide dissolves in water, sodium ions and hydroxide ions go out in the solution. This is why we write them with AQ like this. Now, what happens when the sodium hydroxide is dissolved in water is that a fair amount of energy is released. Heat is given off to the surrounding water and the temperature rises. You can feel it by simply holding the beaker in your hand. We can write a chemical formula for what happens here too. We have the solid sodium hydroxide here. But because the sodium hydroxide doesn't really react with water, it's only dissolved in it, we write water above the reaction arrow like this. Now, aqueous sodium and hydroxide ions form, that is, ions dissolved in the water. But, as I also said, heat is released. We can indicate this by adding energy to the reaction formula like this. We can, of course, draw an energy graph for this reaction too. Let's put the solid sodium hydroxide here. And just like before, to start the reaction, some energy must be added to break the bonds between the sodium ions and the hydroxide ions. As before, this is the activation energy. But note that the ions in this model are not yet dissolved in water, they are not yet aqueous. When the ions become aqueous, new bonds form between the ions and the water molecules, ion dipole bonds. When these bonds form, energy is always released. When the aqueous sodium and hydroxide ions form, more energy than the activation energy is released, which is why the surrounding water heats up and the temperature rises. Since in total energy is given off, the products here, the aqueous sodium and hydroxide ions, have less energy than the reactants, the solid sodium hydroxide. This is typical for exothermic reactions. The second fun reaction looks quite like the first, but instead of solid sodium hydroxide, we instead use solid ammonium nitrate. Just like the first fun reaction, aqueous ammonium and nitrate ions form when the ammonium nitrate dissolves in water. But this time, energy is absorbed and the temperature drops quite considerably. This process is thus endothermic. In this case, when we describe what happens in the reaction with the reaction formula, we must add energy to the solid ammonium nitrate for the reaction to take place. Just like before, we write H2O above the reaction arrow and aqueous ammonium and nitrate ions form. Let's draw an energy graph for this reaction too. Down here, we have the solid ammonium nitrate, NH4NO3S. To break the bonds between the ammonium and nitrate ions, a fair amount of energy must be added. The activation energy is, in this case, quite high. When the ion dipole bonds form between the ions and the water molecules, some energy is released, and aqueous ammonium and nitrate ions form like this. But since the amount of energy released is less than the activation energy, energy is, in total, taken up in the reaction. As you can see, the products, the aqueous ions, have more energy than the reactant, the solid ammonium nitrate. This is typical for endothermic reactions. Now that you've learned what happens in exothermic and endothermic reactions, we can discuss the concept of enthalpy. You see, the enthalpy is the energy content of a certain substance. We write it H and it has the unit joule, or sometimes joule per mole. In reactions, the enthalpies for the reacting substances change, just like I've shown in this video. The change is written delta H and is defined as the enthalpy of the products minus the enthalpy of the reactants. If you didn't completely understand what I mean here, it's okay, because this requires some explanation. I'll try to explain using another reaction, in this case how 1 mole of carbon reacts with 1 mole of oxygen, forming 1 mole of carbon dioxide. We write the reaction formula here too. 1 mole of carbon reacts with 1 mole of oxygen and forms 1 mole of carbon dioxide. In this case, some energy is also released, 394 kilojoules to be exact. Now, what is the change of enthalpy? What is delta H for this reaction? Well, as I said, delta H, the change of enthalpy, is defined as the enthalpy of the products minus the enthalpy of the reactants. In this case, it's the enthalpy of carbon dioxide minus the enthalpies of carbon and oxygen. But what are those? Well, I'm sorry to say, but we can't tell. It's not possible to measure the absolute enthalpies of different substances. We can only measure the change of enthalpy in a given reaction. And as a matter of fact, it's already given here in the reaction formula. For each mole of carbon dioxide that is formed, 394 kilojoules are released. So, in this case, delta H for the reaction becomes minus 394 kilojoules. But hey, where'd that minus sign come from? Good question. Very good question indeed. I'll try to explain the sign of delta H in exo and endothermic reactions. We do this by drawing not an energy graph, but an enthalpy graph, with enthalpy here on the y-axis. In the reaction between carbon and oxygen, we have the reactants here with their enthalpy. As the reaction takes place, energy is given off and carbon dioxide is formed. Because energy has been given off, the enthalpy of carbon dioxide is lower than the enthalpy of carbon and oxygen. And since the change in enthalpy, delta H, is the enthalpy of the products minus the enthalpy of the reactants, delta H becomes negative. I mean, we have quite a small number here, minus a bigger one. The result must then be negative. And this is actually true for all exothermic reactions. For exothermic reactions, delta H is always smaller than 0. So, how about endothermic reactions then? Let's look at what happens when solid ammonium nitrate is dissolved in water again. As the ammonium nitrate dissolves, energy in the form of heat is absorbed from the surrounding solution. Because of this, the enthalpy of the products is larger than the enthalpy of the reactant. And this leads to that the change in enthalpy, the enthalpy of the products minus the enthalpy of the reactant, is positive. Thus, for endothermic reactions, delta H is always greater than 0. So by now you have at least a fundamental understanding of what exothermic and endothermic reactions are and how they relate to enthalpy. Remember to read more and check your learning on my homepage. You'll find a link in the description.